Okay, my lovely physics students. Oh boy, I am, in case you're wondering, yes, I am still wearing my shirt and tie. If you happen to see it on the social media outlets, I was just about to take my tie off, and I thought, no. It is 12:39 on Friday, March 20th, first full day of spring, and I thought, hey, why don't you just go ahead and keep your tie on, even though they will never actually know in this video. All right, I had told you that I would try to make a whiteboard video about worksheet 2 to at least show you like one problem worked out, and as I looked at the backside, this one seemed like the most unusual one in terms of trying to interpret it. So I thought, okay, well, I'll show you this one, and then hopefully my explanation coupled with the key that you already had will hopefully make sense of what's going on. So, without further ado, first, I'm going to draw a force diagram because that's what expert problem solvers do. They draw force diagrams, and in fact, I will draw a motion map. So, force diagram. And let me tell you, this stylus is junk, absolute. Well, it's not the stylus's fault. Oh my gosh, this is a joke already. I mean, I can't even start this thing without having a disaster on my hands. All right, you're gonna have to bear with me. Oh my gosh, the whole freaking thing. Okay. All right, calm down. Deep breath. All right, trying to draw a dot. That is the diver. That is the 65 kilogram diver. And that diver, oh my gosh, there we go. There we go. Oh, look at that. It's an arrow. Oh my gosh, that's That's going to have to be good enough. Wow. That is, we'll call it the force of gravity on diver. This stylus is awful. So that is the force of gravity on diver. Is there any other force acting on the diver as the diver enters, or I should say, falls from the 10-meter platform? I'd say no. That is it. Which means that the summation of all the forces acting on the diver, and in fact this is vertical because we don't have any horizontal forces, this is an entirely vertical situation. So because we don't have anything horizontal, the entire force summation is simply the gravity force, which we know equals m times g. And little g, we know, is negative 10 meters per second. Because, see, that equals ma, and that tells us that little g is a. So a, the acceleration of this diver, as the diver falls from the 10-meter platform, is negative 10 meters per second squared. That's what we know. Got that? Okay. Now, to solve for part A, it says, what is her speed as she enters the water? All right, so after the 10-meter fall, what is her speed? Well, you're going to have to look at the kinematics equations. Hopefully you have them written down somewhere because they are obviously not, well, no, they're still on my whiteboard, but that's on the wall in my room, and you're not there. Nor am I, in fact. So, I would choose this one. If you're looking, or maybe we should make a list. You know what? Let's make a list. I mean, it's been so long since we've done this. We have VF, we have VI, we have A, we have delta T, we have, oh boy, we have delta X. Is that it? Delta T, oh my gosh. No, I already had that. Oh boy. Yeah, I think there's just 5. So, if those are our variables, what do we know? Well, this is what we're looking for. We want to know the final velocity. This, we know at least I'm assuming. I mean, when you leave a platform, you're not moving vertically. So you start with 0 meters per second of velocity. And then the acceleration, we just said, was negative 10 meters per second. Oh boy, per second squared. And the time, well, we don't know how much time it's going to take to fall. I don't know that we need that. And then the delta x, we know that the diver is going to fall 10 meters. Now, what direction is that? Well, down. And if we're saying that the acceleration is negative, then the delta x should also be a negative 10 meters. All right, so that's what we know. And you know what? We should draw a darn motion map, because that's what expert problem solvers do. So let's say that's the water right there. And let's say that up is positive, down is negative. And so this diver is starting with no velocity, or I should say very little, at the first second, and then the second, and the third second. And so the velocity is obviously getting bigger. Oh boy, can I get another one in here? Oh, look at that. It's not that much bigger than the previous one. It'll be okay. A is down. And again, down is negative, and so there you have it. There's the motion map, which matches, again, it matches the force diagram. Force diagram shows only one force acting, and it is in the down direction, which means our acceleration, because again, we have unbalanced forces, our acceleration also has to be in the down direction. And that's what we see from the motion map, which agrees with our force diagram. Now, the equation I would use this one. Oh, let me stick with red. VF squared equals, oh my gosh, equals VI squared plus 2A delta x. All right, so there's that equation right there. Plugging in all the stuff that you know. So again, you're looking for VF squared, or VF I should say. And so we know the VI squared is 0, so that's gone. Then we have 2 times our negative 10 meters per second squared times our negative 10 meters, which is going to give us a velocity of 14.14 meters per second. Now, if you remember anything about this from before, that velocity right here, let's see, that velocity is in the downward direction. Downward direction. Oh my gosh, my stylus is literally coming apart as we speak. Okay. I'm going to have to build my own or something. This is terrible. So we have a negative velocity at the end, but notice this equation can't give you a negative because it's under a radical here. So you have to remember that the answer here is, it could be a positive or it could be a negative. And in this case, it is definitely negative. So make note of that on your paper, in your information, whatever. Unless you said that down was positive, I suppose you could have done that and said up was negative. And in that case, both the signs would be reversed and you would have a positive velocity. I don't like the way that negative sign looked. All right. Next, part B says she comes to a stop 2 meters below the surface of the water. What net force did the water exert on the swimmer? Now, by net force, what do we mean? We mean the amount of imbalance. So, for instance, let me draw a force diagram, or maybe you should. I don't know. Yeah, maybe you should. Here's a force diagram of the diver after she enters the water. Once she enters the water, is there still a gravity force acting on her? Yes, there is. There is still a gravity force acting on... Oh, I drew it kind of short, didn't I? Oh, gosh. Okay, just pretend that that's the same length as the other one. I don't care. But as she enters the water, there's also now what's called a buoyant force, or a force of water on the diver. And that's got to be bigger than the gravity force. Now, I didn't do this yet, but let's just say if, because, expert problem solvers sketch motion maps too. So if I'm still saying that up is positive and that she got to the surface of the water, which was my 0 position, now she's going to be entering the water, and she's going to be entering the water with what? A large velocity. So she's starting at the water now with a big velocity, and what's happening to the velocity? It is decreasing, and so then my arrows get shorter, and now my A is what direction? I hope you're thinking up. So my acceleration is up, and because my acceleration is up, that should tell me that my force diagram has to be unbalanced up. In other words, the force of the water, which I didn't even label yet. So the force of water on diver has to be bigger than the force of gravity on diver. Okay, now, but again, that's not even what I was trying to figure out here. What I'm trying to figure out is what is the net force the water exerts on the swimmer. Now, they're not asking for how much force the water exerted. They're asking for the net force. What is the net force? The net force is the unbalanced force. Whenever you see the term net force, you need to remember that means unbalanced. Unbalanced force. How much unbalanced force is there? Well, how do you find that out? Well, you look at a summation. Well, in this case, for this part of the problem, we have, again, a vertical summation. We have gravity force acting down. We have water force acting up. And what do those equal? Well, they equal ma. Now, which one of these is the net force? Like, is that net force? Is this net force? Is this net force? I'm going to say that's net force. That right there. That is net force. The amount of imbalance. And how much imbalance is there? That plus that. So that plus that is the imbalance. But we don't know what that is. We don't know how much force the water exerts. Do we know how much force gravity exerts? Well, yeah, because we know that she's 50 or 65 kilograms, and we can figure out how much the gravity force is. But we have no idea how much the water force is, and we don't care how much the water force is. What we care about is how much is the gravity force plus the water force. So again, we don't really care about either one of those individually. We care about them combined. I hope this is making sense. So that means the way I would view it if I were you, and I'm not, but if I were, I would say that the sum of all the forces acting equals ma. This is what I want. I want to know what that is. The total amount of force, or sum, or net force is what I want. Now, there's only one way to find that at this point. Well, actually, there's two ways to find it. The one I just said was we need to know the gravity force and we need to know the force of the water. We know the gravity force, we don't know the force of the water. If we had both of those, we could simply add them and then we would see what this is. So because we don't have this, that's not an option. What's our option? We have to know ma. We have to know how massive the diver is, and we have to know how much acceleration she experiences, easy for you to say, as she slows down in the water. Well, do we know what A is? No, we don't know what this A is. What do we know? Well, we know how fast she is when she enters the water. We know her velocity here. Oh. So the final here that we just found in part A becomes the initial here. So now we have to do a whole other problem with this information based on what we know now in part 2, or the second part of the problem. Oh my gosh, do you see how complicated this is kind of becoming? And I don't know if it's all that complicated, but I mean, I don't know. Hopefully this is helping and making sense. I can't believe it's 15 minutes already. It seems like I just started. Oh, let's see. Hold on. What am I doing? Oh yeah, I'm making a list with my diagram. Okay, so here's what we know. We know that the velocity here, the initial velocity as she enters the water is, oh no, you know what's going to happen? This whole thing, oh no. I need to move the toolbar. I don't know how to move the toolbar. How do I, there, okay, there we go. You can't see it. See, you don't know the toolbar is on my screen right now, and it's in my way. I cannot write on the screen where I'm trying to write on the screen because my toolbar is in the way. So I'm going to say that that's the 14.14. Oh no, I can't put the unit of measure on there, and you know how much I hate that. Meters per second. Oh gosh. Again, you don't see it, but the toolbar is in my way. Oh, it changed to highlighter mode. Oh my gosh. Okay, anyway, 14.14 meters per second. That is now our initial. What is our final down here? Because again, at the bottom, in the water, she's going to stop. And so that's 0 meters per second. That's the final velocity. Next question. How far is this? Oh, she comes to a stop 2 meters below the surface. Okay, so that's 2 meters. Okay, so we should make our list again. This is going to get messy. This is getting really messy. Hold on. I have to, oh gosh, the list. Can I just write it over here next to the other list? Yeah, let's do that. So now my final velocity is 0 meters per second. My initial velocity is negative 14.14. Why is this there? Meters per second. My acceleration is still, oh, no. Oh my gosh, that's not true. I don't know what my acceleration is. We need that. We need this. Delta t, I don't know that either. Delta x, negative 2 meters. Okay, so are you seeing here? No, again, I kind of scribbled all this. So again, that's a variable I know. I'm stopping. Starting at negative 14.14 meters per second. I don't know how much acceleration. I need to find that. And then negative 2 meters is the change in position. So it looks like we're going to need the same equation that we used over here, only now we have some different information for the end. And so final is 0. So I have 0 equals, what is wrong with this stupid, I got to get a new stylus. Or build one. Where was I? Oh yeah, negative 14.14 meters per second, and that's squared, plus 2 times negative 10 meters per second squared times negative, oh my gosh, oh my, this is such a pain, negative 2 meters. Okay, and then all that gives me, oh no, what the heck am I doing? Oh my gosh, hold on. Can I erase this? Okay, good. We don't know that. That's A. We don't know the A. We're trying to find the A because we need the A to use here. Okay. Hopefully I didn't lose you or confuse you. So that, when you do all that math, you get the A is negative 50. No, not negative, you bonehead. Not negative. It's 50 because it's up. Remember, it's up this time. So it is 50 meters per second squared. 50 meters per second squared, and that's up. Okay, so now what? Oh gosh. I'm noticing that there's way more on my screen right now than what's on the actual key, I think. I feel like there's more here. All right, it's almost done. Here we go. Now we use the A that you just found. That is this A. 65 kilograms is this M. That's it. And that equals this, which is what we're trying to find. Okay, so summation, or the net force is, all right, this is going to be the last video I make with this stylus. I'm telling you right now. It is junk. Have I said yet that this, I'm not sure if I told you yet, but this stylus is junk. 65 kilograms times, I feel like I have to write so slow with this thing, times my 50 meters per second squared is a net force of 3,250 newtons. That's the net force. Now, again, follow with me here. That is not how much force the water exerts. That is the force of gravity plus the force of the water. Well, what if you want to find out how much force the water actually has to exert to produce this much net force? Well, then you'd have to put that amount here, put your gravity force in here, and then solve for the force of the water, which is going to be even bigger than this value. So the water, you see, the water has to push not just against the gravity, but also with this much extra. Because the extra is what causes the acceleration. If the water just pushed with as much as gravity, then the summation would be 0 and we would have no acceleration. Hope that's making sense. Again, if the water only pushed up with equal force to what gravity is pushing down, then we would have balance and we would have no acceleration. So the water has to push with a force, gravity, plus more to cause an acceleration. And so if you want to think of it this way, maybe this will give you a visual. Let's pretend I'm going to draw a red arrow here in the force diagram that goes up. Let's say that's how much force the water has to exert just to balance out the gravity force. This is what you actually solved for. Maybe a visual helps. So that's what gravity's doing. That's what the water had to do minimum to actually balance gravity, and then it had to do this much more, that much more, to make there be an acceleration. And that's what this value is. I hope that makes sense. Now that we're almost 25 minutes into this, holy mackerel. You probably didn't know you were going to get into this. But that's kind of how you have to approach these, all right, one thing at a time. Again, sketching or pictures, which I didn't actually do, drawing force diagrams, motion maps, writing out summations, like all the same stuff we were doing before, only now we have imbalances which are causing accelerations. I hope that will help with the rest of this worksheet if you haven't already done it. Now what you could do, I'll just leave it at that. If you have other questions on the rest of this thing, then be sure to let me know. Signing off, Mr. Dilbum. See you later.